Since we are a couple of minutes after the hour, I think we should go ahead and get started. So Doriana is going to give us a talk about some of their workflow work, and she's from the University of Torino. And with that, I'll let you introduce yourself and what you're talking about today. Thank you.
Okay, thank you. Hello, everyone. Good morning, good afternoon, depending where in the world you are. So I'm Doriana Medic. I am assistant professor at the Computer Science Department of the University of Turin. And here I will give a talk about the workflow orchestration and about the bridging HPC and HPC and quantum. So let me just say a little bit about the place where I am. So I'm the part of the Alpha Parallel Computing Group at the University of Turin. And this is a very heterogeneous team with expertise that are spanning multiple areas of computing. So our research activities are cover a broad range of topics reflecting the diversity and interests and the backgrounds within the group. So I'm like mathematician. We have the chem people that have a chemistry degree or physics degree, of course, also computer science degree, engineering, etc. So the main topics that we are interested are high performance computing and parallel programming, RISC-V and the next generation architectures. Can you hear me? I'm sorry.
Yes, okay. Can hear you just fine.
Okay. So then HPC system, software, and data-intensive computing. So like workflow management system, distributed execution across HPC, cloud infrastructures, and the quantum, scalable storage solution, and etc. Then we have cloud computing and the virtualized infrastructures, artificial intelligence, federated learning, distributed AI. And lately, we are also interested in quantum computing. So hybrid quantum classical application, workflow systems that are integrating the classical and quantum resources, quantum machine learning, and quantum optimization. So here I will actually, in this talk, I will talk about the workflows, so distributed workflows and intersections between workflows and quantum computing. So in the beginning, let me give just a little bit of motivation. So over the last year, the demand for computing power has grown dramatically. We all saw, while HPC systems have been traditionally used to support scientific simulations and some engineering applications. Now increasingly they're required for training and deploying large language models, foundational models, AI for science, complex data-intensive workflows, and etc. As a result, of course, many governments and research institutions worldwide are continuously expanding their HPC infrastructure. So, for example, in Europe, this trend is particularly evident through a Euro HPC joint undertaking, which is investing not only in the supercomputers, but also in AI factories to integrate AI and HPC and cloud technologies, and lately also quantum computing. So in 2026, like more than 10 billion public investment is invested in Europe in AI gigafactories that want to integrate AI and HPC and to highlight the strategic importance of computing infrastructure. At the same time, of course, the quantum computing ecosystem is rapidly expanding, so the numbers of available quantum computers continuously grow, both through the cloud providers, but also national infrastructures, also with several quantum processors now being integrated also along traditional HPC systems. So many dollars, billions of dollars are invested by government, by China, by US, by Europe, even in this kind of computing power, so quantum and HPC. So especially, for example, in Europe, is pushing a coordinated strategy to quantum flagship and Euro AKPC, while Italy is significantly strengthened its position through National Center of High Performance Computing, Big Data, and Quantum Computing, and integration of quantum resources at Cineca. So, what clearly emerges is that computing infrastructures are becoming increasingly heterogeneous. Instead of relying on a single supercomputer, future application will have access to rich ecosystem of CPU, GPUs, cloud resources, AI accelerators, quantum processor, and etc. However, simply having access to all these resources does not automatically make application faster or easier to execute. In fact, all of this introduces an entirely new level of complexity. So, all these investments, but why? The reason is that applications themselves are evolving. So modern scientific but also industrial applications are not anymore monolithic programs executed on a single machine. They have become complex computational pipelines composed of many interconnected stages. So a typical application may involve data acquisition, preprocessing, large-scale simulation, machine learning, optimization, visualization, post-processing, etc. And each stage produces data that are becoming the input of the next one, creating the complex dependency graphs. Moreover, these stages have very different computational characteristics. So a numerical simulation is naturally executed on an HPC cluster. Training a neural network benefits from GPU. Data processing could be more efficient on cloud, etc. The optimization problem may exploit quantum processor, and etc. In other words, different parts of the same applications are best executed on different computing resources. So, what this means that there is no single computing infrastructure is sufficient anymore. Instead, the applications will need to seamlessly combine multiple execution environments, and maybe also selecting the appropriate resource for each task, while efficiently managing data movement and also execution dependencies. Therefore, we are moving from isolated system to connected ecosystem. So application can span multiple computing environments, including HPC, cloud, edge, AI, accelerators, quantum, and etc. So what is the challenge? So there is no longer the challenge is no longer simply executing the application on a powerful machine, but the challenge is actually orchestrating complex application across a heterogeneous ecosystem of computing resources in a transparent, efficient, reproducible, and portable way. So in this talk, I will talk about one of the solutions for this, so how we can actually do it. So through workflows. So I will talk about how we describe the workflow or what are the workflows in general, the centralized orchestration of the workflows, decentralized orchestration, and about QSplit, that is our framework that integrates quantum and HPC execution. So starting from workflows. So all this evolution that mentioned like in previous 5 minutes has led to widespread adoption of the workflow paradigm. So rather than describing the application as a single program, workflow represents a collection of interconnected steps together with their data, so inputs and control dependencies. So we can see as a workflow everything. Workflow can be a business model, can be a recipe how to make a pizza, can be any kind of experiment, and etc. So what actually in general workflows provide? So they provide abstraction. So they allow researchers or anyone that is using them to focus on a scientific logic of the application and not on the high-level execution details. Then they provide automation, so taking care of scheduling tasks and managing data movement, allocating resources, recovering from failures, and etc. Then portability, because by enabling the same workflow to be executed on different computing infrastructures. Is it a HPC cluster, cloud platform? We saw now we have a wide set of different structures, and we need somehow to make this transition from one to another infrastructure easier. And reproducibility. So these workflows, of course, they allow you to repeat the experiment and to execute the same computation path multiple times under some controlled execution, and etc. So, of course, we are concentrating mostly on the scientific workflows. So what is the scientific workflows for us? It's a formal representation of some computational application. It is typically modeled as a directed acyclic graph, but we saw also with federated learning and etc. It's just directed graph because often we can have cycles or loops inside. So vertices, for example, here, in general, they're presenting like steps or tasks that should be computed or executed, while the edges are defining the dependencies between these tasks. So each activity can perform a specific computation, such as data preprocessing, for example, simulation, model training, optimization, etc. And it produces outputs that then become an input of subsequent activities. So this kind of representation naturally captures both the execution order and the opportunities for parallelism. So how we can see, this is a small example of one workflow model. So this is one simple cyclic graph. So what are the components of our workflow? Let me just repeat. So we have tasks or steps. Then we have a ports. This is like address where I can find the data as I input, or where the data is when I save the data, when I produce it. Then we have the data, of course, input or output data, and we have dependencies between the tasks. So this is we can say that now we have actually defined the workflow model. We did not define any kind of deployment or any kind of execution, just the application and all the computation the application needs to do. And now we can on that add hybrid workflows. So the hybrid workflows actually separate or on what application does, what would be a workflow model, to where and how this application is executed. So once application is described as this kind of dependency graph or any kind of model language that describes the workflows, then the workflow management system should determine how this workflow will be deployed, should be deployed on available computing infrastructures. So these like hybrid workflows actually are very interested. Are becoming very interesting, very important in computing continuum, because we will have different workflow activities that can be executed on HP system, cloud resources, GPUs, and etc. So to make this workflow hybrid, we add locations, of course, or computing environments, resources that we have. So some kind of location topology. So we need to know how these locations are connected. And then we map each step to location where it should be executed, as said before. So if it's a training, maybe we would like to be mapped on GPU. If it's some lighter step of some data processing, maybe on cloud, and optimization, maybe on quantum computing, and etc. So this kind actually of hybrid workflows clearly separates workflow model from the environment. So why this is a very interesting is because if we would like to change, and in this case, maybe step S4 would like to to connect it maybe to location L3, not L2, because I don't know, for some reason it is unavailable, then we don't need to rewrite the whole workflow. We should just rewrite or change the mapping between step and the location. So, having described the workflows, we considered two types of orchestration of the workflows. So, first one that we see is centralized orchestration. So, a single orchestration engine is responsible for managing the entire workflow execution. The orchestrator maintains the global view of the workflow state, so it has all the knowledge about the workflows. It coordinates the task scheduling and controls the interaction between different resources or execution sites. It checks if the tasks are executed, if the data is produced, and etc. So this approach, of course, has many advantages. So the centralized view enables more informed scheduling decisions. It simplifies monitoring and logging. It benefits from mature orchestration frameworks and tools that have been developed over time. So many workflow management systems are actually centralized. So they have a central controller, as we can see on the image, that actually have a knowledge of our workflow graph, let's say, and then with some kind of maybe, depending in this case, I said kind of configuration, but it can be in one file altogether, I don't know. It decides or it just deploys what is written in the configuration and maps different steps to different locations. So, however, this centralized orchestration also can introduce some limits. So the orchestrator can become a single point of failure. And the continuous communication between the central engine and the execution sites may introduce additional overhead. And furthermore, execution sites in this case have a limited autonomy, as decisions are primarily and only driven by the central component, actually, rather than being managed locally. So for this kind of orchestration, we our research group actually developed the Streamflow, so workflow management system that is designed to support execution of complex scientific workflows across heterogeneous computing environments. So Streamflow is CWL compliant, so common workflow language. I will say a few words about it in the next slide. So this is a language that actually describes the workflow model as we could see before. So it does not say where it be deployed or which resource. Is just it just describes the workflow. Streamflow is container native, so it allowing application and workflow components to be packed and executed consistently across the different infrastructures. This facilitates, of course, portability and simplifies the deployment of complex application. The particular nature of Streamflow that it is designed in a modular way. So the new environment actually is added as a connector to Streamflow, and it is not necessary to change actually the core of the workflow management system, but only to add some kind of plugin. So it already has developed different plugins, so for different environments. So we have Slurm, we have Container Docker, Kubernetes, and etc. And lately, we are also developing different quantum connectors. Streamflow is also used in many different projects to execute different types of applications, from astrophysics to bioinformatics, in some cases even federated learning and etc. And lately, this workflow. Okay, let me say a few words about common workflow language. So first, So Common Workflow Language is an open standard for describing command line tools and connecting them together to define reproducible workflows. It provides a common way to specify how applications are executed. It includes their input, outputs, parameter dependencies, etc. But it's not actually. It is not deploying them on different infrastructures. So of course, having a common workflow language, it is portable. So tools and workflows described are in standard way, and they can be executed on different platforms. And this CWL it facilitates scalability, so it allows complex data analysis and, for example, machine learning workflows to move seamlessly from the developer's laptop to some HPC large-scale computing infrastructure. This is I will just say a few examples of how we use StreamFlow. So in this case, we use it to orchestrate the cross-facility federated learning. So we have two LLMs. One, it was on Cineca Leonardo. Another one was at Carolina. They are both trained on the different languages, so Italian and the Czech Republic one. And they are so the illustration was these two clusters, and the aggregation was done on the cloud of Cineca. The training is done on the two HPCs, then the data is aggregated, then the trained model are then aggregated, then some kind of metrics are done, probably the average, and then the new model is sent again, then trained again, and etc. Then we use also StreamFlow to orchestrate ML workflows on the top of cloud, HPC, and private execution environments. So in this case, we did it with Italian agency of taxes. So it was Catasto. So they were interested actually to look into orthographic photos and to see which buildings are not in Catasto. So to find illegal buildings, illegal swimming pools, and etc. So, and they were, this is the application wise, while the system wise, they were interested how they can actually integrate one HPC center or use somehow public HPC center as Leonardo, or in this case, it was our HPC cluster, to actually offload some computationally complex training. So we orchestrate this kind of pipeline with StreamFlow, where all the yellow part was private, so we could not access it, and it was quite complicated. So my experience in connecting the public and private cluster was quite complex, because they have a completely different idea of privacy and everything else. And lately, StreamFlow is inside of the Italian AI factory. As I mentioned in the beginning, European Union is providing a lot of resources to different countries and building AI factories. And StreamFlow will be the asset at the new machine, that new supercomputer that will be built in Cineca. And with that, I will go to the QSplit. So what is actually QSplit? The QSplit is a work-oriented hybrid quantum classical optimization framework. So it's practically, we used StreamFlow and we orchestrated workflow that is able to dispatch different tasks on HPC, cloud, and a quantum machine. So as I said. So it's a Wolf-oriented hybrid quantum classical framework. It targets problems that are expressed in a Kubo form. I will explain later in more details. And it is the framework, its goal is to address the limitation of current quantum devices and the complexity of large-scale instances. So QSplit applies the composition strategy. It splits large optimization problems into smaller sub-instances that can be actually efficient processed, and that can fit to nowadays QPUs. Then it dispatches them, as I said, to different backends, so quantum simulators on HPC and actually quantum real QPUs, and in this case we use the EQM-Swan. And finally, it combines the partial results and reconstruct the global solution. So let's see how this actually looks. So we take the data set that is that has many instances of Kubo matrices, so the Kubo problems, and it dispatch them, okay, as we can see. And then for each instances, it triggers or spawn like a parallel thread, let's say in this case, parallel process that will actually solve this Kubo problem. So Kubo problems are going from small one to the 1,000 variable one. And then at the end, it collects all of them. So what is actually inside of this one solver instance block? So this is the real, the splitting part. So we have the first time we take some Kubo problem, then we split large Kubo instances into smaller one. Then they are like solved with different algorithms. So we used CUDA-Q and we use IBM Quava algorithm, also annealing, and etc. And then we actually aggregate all these small results into a global solution. So this is the part of the workflow model, and this is the part that is described in CWL. And then we orchestrate that with the stream flow. So how it looks a little bit complicated. So let's see how we actually did it. So we have these 4 resources. So we have cloud resource, we have simulation, I think CUDA-Q that it was on GPU, on HPC GPU. Then we have like IBM that we put on HPC CPU, and then we have a QPU that we at that moment we have like access to EQM machine. So how we did? So we dispatch and collect, since that are the tasks that are really light, we put them on the cloud. Then we had a split part. So we spawn for each Kubo problem, we spawn a split element. So and that split task we put on the HPC since it was computationally more intensive. Then
sorry,
we have
sorry to interrupt.
Yes.
I have a question.
Yeah.
How do you do the decomposition of the problem into sub problems that you run them on different backend? Like when you know, I don't think this is clear to me how you do this dispatching. You know, do you have a sub routine that finds the quantum prone sub problems, or how do you do that?
So practically we have a matrix, no? So we have a Kubo matrix, and then we actually split the matrix into smaller matrix. So in this case, we did it recursively. So if you have a matrix, I don't know, 2, 4 to 8 by 8, then you would split it at 4 quadrant and etc. So recursively you're splitting it until you I don't know, depending how big you want the small matrix to be. So practically it's a kind of decomposition model, the easier one.
So it's kind of a load balance decomposition where you don't necessarily find a sub problem, because they're kind of each problem has its own natural structure, where certain variables are more tightly kind of connected, either from the graph connectivity of problem or that because of
Yes.
the frustration in the problem. So you're unaware or are not including those. It's more of a load balancing cut.
For now, we are not including. Well, in this case, that I will say, we are not including that. But then, actually, we are looking to include it, since I will show that our results show that depending on the matrix, so how many connection you have between the variable, actually, so if the matrix is sparse or not, we are more or less like the classical solution. So we were actually measuring how far this kind of splitting, so decomposing or splitting the problem into small instances, then solving them, then aggregating them. Of course, it's not that you are exactly like you would do all the instance on HPC. So you're somehow approximating your result. So more, we are now trying to see, because with different problems, we are realizing that different kind of decomposition works better.
Yeah,
So
so
in this
I
case,
just
we
want
use
to tell you
only
that this
one.
is highly non-trivial problem. We've been working on it for more than 15 years, and it's just much harder than you think. Okay, so the other things that I want to tell you, I mean, despite thousands of paper on QAOA or annealing, I just want to like emphasize for people here on the call, Kubo formulation is really a kiss of death. Like, if you're only married to that, the embedding that, the embedding overhead, people usually discuss the embedding overhead of a Pubu to Kubo formulation, but it actually changes the complexity of the problem itself. So it changes, like in annealing kind of framework, it changes the gap, the quantum Hamiltonian gap significantly. Basically creates like unusual correlations of variables because of the embedding, which is basically changes the complexity of your problem, not only the overhead. And that applies to QAOA or any other formalism. So you want to be as close to the native formulation as possible. With that in the background, do you have any fundamental limitations to go to PUBO, like a higher order polynomial, instead of second order?
Okay, we are not developing a new algorithm for solving Kubo or something. We are just decomposing the matrix and then giving it to the
No, but can
already
the matrix
existing.
could be in the PUBO for no, so it doesn't. What is the fundamental limitations that should be second order interaction? Could that have higher order nonlinear terms?
So since here we are actually describing the workflow, the inside of this split task, you could define some script if you want that will split your Kubo or something, and then it's okay. We are not still working on transforming Kubo into Kubo. This is only the orchestration of the decomposition. It's not going inside of the Kubo. So only splitting it, not defining exactly the Kubo
No, but I think
matrix.
earlier slide you had only works for Kubo formulation, or maybe I
For now,
misunderstood.
for now, for now, this is our
Okay,
use case. Okay,
okay,
so we will. I think we already are looking a little bit to transform or to try to see if we can transform matrix into Hubo and then try to see if some kind of decomposition could work. But in this work, principal part is actually the HPC and quantum integration and the deployment of
okay,
decomposition, the
okay,
steps
thanks.
that are split.
Got it, thanks.
So yeah, so this the split of the steps of splitting and aggregations, we deploy them on HPC cluster, and then we have all the inside as like the composition as was mentioned. So the small split small parts of the matrices that are dispatched to different backends. So some of them we dispatch to real QPU for each instance. So for each, in this case, Kuba matrix. Then some of them go to the solvers on HPC with CPU, and some of them on the solvers on HPC with GPU. So this kind of, so our results that, as I mentioned, so we have like max cut problem that is more like sparse problems, and with less variables. So more or less here we can see like a green and a red dot, and we are looking actually that are representing the solution. So we are looking the distance between green and a red dot. If we see only one dot, that means that they are overlapping. So more or less the solution is let's say consistent with simulating annealing when we increase the problem dimension, while we are testing different problems and maybe where the matrices are not so sparse, and we can see that in a certain point actually this connection is getting this distance is getting higher and higher with if the problem dimension is higher, not actually the problem dimension, but it's percent, it's the the percentage, the actually the percentage between the how problem is large and how much we need actually to split it. So because if we have problem on of 100 variable, we can split it to 2 and then execute, or we can split it 10 times and then actually aggregate and try to find the unique solution at the end. So I would just like to say about the QSplit, but actually I will say it for the future work, because we are looking, this is a framework that is quite general. So all these steps that I was mentioning, this is more or less like scripts that you call from the workflow. So VS, in this case, we are using a Kubo because we have this case study. But any kind of a problem that you have, it can be done if you have the scripts actually to call. So if you have your computational task and you know and you already have it written or code for it, it can be easily and it has a structure more or less like this that you can decompose it and then aggregate it. It easily can be implemented or orchestrated actually in this kind of framework. And for the end, I would just say a little bit about the decentralized orchestration. So in a decentralized orchestrating approach, workflow control and decision makings are distributed among multiple components rather than actually being managed by a central server or a single orchestrator. Each component can independently coordinate their tasks, make scheduling decisions, interact with available resources, and enabling a more autonomous execution model. So this approach that have several advantages. So by reducing the dependency on the central controller, decentralized orchestration can lower the communication overhead and enable faster local decision making. So it also improves the resilience by avoiding a single point of failure. And it allows different execution sites to maintain greater autonomy over their resources. This can be useful when we have a different, many edge devices that communication with the central server actually would be a bottleneck, and sometimes, if depending on how big, how scale is, it is a bottleneck. However, this kind of approaches, of course, has also challenges. So since no one has a central point of view and no one knows all, no one has knowledge about the whole workflow, achieving global optimization and coordination is not so easy. And of course, also achieving the fault tolerant system is not so easy, because if one location is down, it is, and there is no one to check if this location, and no one knows what this location should do and what task it should execute. It's difficult actually to recover it. So here we also developed a scientific workflow intermediate representation language. Actually, in this case, We are designed to bridge the gap between the high-level workflow descriptions and the low-level execution environments. So it provides the intermediate representation that enables the optimization and deployment of scientific workflows across, again, heterogeneous computing infrastructures. So the compiler actually translates, in this case, Pegasus. We are working still on CWL. It translates the workflows that are written in Pegasus into the Swirl. Then they can be Swirl are like simple process algebra, like very formal method workflows that has where each location has a different trace. Then it can be optimized since it's a simple send receive actions. It is represented by simple send receive actions, and then it can be actually provided to it can be compiled into a distributed executable bundle that is tailored to a specific target environment and actually then dispatched to the environment. And all the necessary information that one location needs to know, it's inside of the bundle. There is no one that is actually controlling the execution, and we tested it on Genome workflow. So the idea is to actually to decrease the time of the communication in different workflow executions. Also, we are working on agentic workflow on a Swirl-like system. So developing this formal kind of system and formal semantics for Swirl, we actually realized that introducing AI into workflow management will introduce new challenges that we need to ensure autonomous decisions are correctly translated into executable workflows. So from a verification perspective, it's focused on guaranteeing that the intent expressed by user is preserved through the entire workflow lifecycle, from high-level listening to the infrastructure level execution. So the idea is actually to use like a Swirl-like system and to control, to give a certain policies what an agent can do and what not. If an agent will to call one workflow, it can. It probably maybe wants to change some parts of it for a different reason. Maybe that could be many. It can try to change, but every time he needs to somehow this change need to be correspondent with actually the policy of user, or I don't know who is making the policy creator. And so key takeaways are that application in general, scientific, industrial, etc., are becoming heterogeneous. We developed two, let's say, workflow management systems. So high-level Streamflow as an orchestrator for a hybrid workflows that is integrating HPC, cloud, and quantum. We have a QSplit framework. So it's a workflow for the composition of large optimization problems that can to be able to fit into QPU compatible problems. So in our case, the matrix that we want to obtain, mini1 is a parameter, so it could be changed. So if now it's, I don't know, 10 rows, it's easily transformed into 1,000 rows. And then we developed as well an intermediate language for decentralized workflow execution. Interest. So what was mentioned before, we would like to extend QSplit in different directions. So one of the direction is to add a new backend. So we tried already with Continuum backend. And we will try to do it with Pascal machine, etc. So another one is a new decomposition strategies, because not each problem can be efficiently decomposed and then aggregate with the decomposition strategy we have. So we are trying to find a new one, and we are extending QSplit to be like parametric to the strategy we want to use. So somehow to find to determine the problems that can be for which we can use different kind of decomposition strategies. Also, we are looking into different use cases. So we were thinking also circuit cutting, because in this case, again, we could somehow cut circuits. So within a split part, we could be able to cut circuits, then dispatch them maybe to some different backends and then aggregate the results, but we are still working on this. Then we are interested into applying a QSplit framework into different multi-QPU scenarios, so any kind of applications. We are interested in quantum machine learning, quantum optimization. We are investigating different direction in quantum optimization, looking into different mixers and etc. And we're interested also in extending Sphere. So we are developing the translation from CWL into Sphere. So idea in a global level is that if you have a workflow that is written in one language, you would be able to orchestrate it maybe centrally with Streamflow, and maybe if in that case you have the overhead is too big, maybe then because depending on the application used considered, it could be also orchestrated decentralized by using Sphere. And that's it from me. Thank you for your attention. I don't know if you have any questions. I would just.
Thank you. So I've got a couple of questions, but I'll let others have a chance first.
Maybe I can go first. Could you tell us a little bit about your quantum circuit cutting strategy, and then how you're thinking about it?
Okay, this is really work that we are just looking into it. So I, unfortunately, I cannot tell so much, because this QSplit is actually made for, as I said at the beginning, for Kuba problem. But then we realized that we could be able to expand it to different use cases.
Yeah. Great. Yeah. Yeah, we'd be very
maybe
happy to
I would be, maybe in a few months I would be able to tell you more about quantum circuit cutting.
Yeah, sounds good. I mean, we think about it quite a lot, especially using entanglement as a guiding metric for circuit cutting. So we'd be very happy to chat at some point if you'd like.
We are, I'm sorry. We are interested also in orchestrating all this, because what we realize that already some people are working on that, and I suppose they're working on that for years. So they have, but we are actually interested in orchestrating all this pipeline. So if I understood, there is a different pipeline where you need to cut the circuit, then somehow you solve the problem. And for me, it was very similar to this kind of decomposition, then dispatching the parts to different backends and etc.
Right.
So if you are interested in somehow automatizing this part, or trying with multi-QPU execution or multi-HPC execution, we are really interested into it.
Yeah, so I just want to say that at HP we have been thinking about this long and hard, and the advantages in doing it correctly, like when you go beyond simple like load balancing or naive circuit cutting, or just gate by gate cutting, as like minimizing the number of CNOT. These are all kind of pretty primitive approaches to circuit kneading or circuit cutting. The difference is not like we are 10-20%. We are talking about significant reduction. So it could be a quadratic reduction in the exponent over as naive circuit cutting for electronic structure Hamiltonian. it would be a quadratic. Even if you want to use quantum interconnect, it's a full quadratic reduction in the quantum interconnect. If you want to apply to transfer sizing model, it could be exponential improvement. So that means applying to, for quantum optimization. Basically, what it happens that the communication between different QPUs would be exponential if you just are unaware of the kind of classical quantum correlations in both classical spin glasses and quantum version of transfer sizing model. So it's just generally if you would get into really cutting across the blocks of variables that are strongly have to communicate. So you have to pay exponential price for cutting it, and it won't work. It's just not like you improve a small improvement. It basically the difference is to get it to work or not. I'm saying that you need to be aware of the correlations when you do any circuit cutting. And sometimes they're adaptive and should be done in real time.
Okay. Thank you.
Thanks.
So, so I had a side question. Actually, I saw in one of your points about the fault tolerance. This is less about the quantum piece, but more about your system in general. Do you see that you need any new primitives like consensus or things like that, or do you just put those in a node and that's just another task?
For now, we're just putting them on the nodes and that's it. But I think we will need something, honestly. So now it's just easily I give you all the, let's say, trace of the workflow, the whole part of the workflow that should be executed on this location and go.
And another one I had was the scheduling aspects for sort of dynamic behavior coming out of systems. Do you guys surface that, and how do you feed that in to scheduling decisions along the graph so that things are coming and going and so forth?
Are you talking about the quantum HPC part, or?
It would really be for any computational resource. I mean, it could be that it's slower than anticipated, or it's coming and going, or maybe you're assuming that things are always connected. Just some of those properties, specifically about large differences in time is what I was sort of dynamic behavior.
Okay. Now we are for the quantum part, because Streamflow actually has its own scheduler and it's already like managing different parts of dynamic scheduling. So if the location is down, if the queue, depending of the queue swarm is big and you have other options, maybe you will send it to some other machine and etc. And also it has you can implement different topologies. So some locations are not necessarily connected by between them. So the data or that need to pass through different locations. So not directly from one to another. So you kind of calculate the fastest, some kind of fastest path, however you want. When we integrated the quantum part, for now, so we actually needed to extend all these different parts of Streamflow. So different connectors, we needed to add the connector, then we needed to extend the policy and also to include the scheduling part. So for now, it's assumed that everything is connected, but it should be actually integrated better into the Streamflow scheduling. We are also realizing that connecting to different backends means having different information. So we need also for Quantinum, we have different plugin and etc. So for Pascal, I would expect, I know we will have a new one and like this.
And other, just from what you said there, other events that would be specific maybe to quantum would be this calibration idea that you now need to go back and revisit parts of the graph. How do you guys, do you adapt that into things, is bringing those factors in? So a node that
it's kind of loop. So I imagine it kind of loop. So I give some job to quantum machine, then I gave some results if I understood. It gives me some output, then I need to do some work, and then I need to give it again, and like this. Yeah.
Yeah. I'm sorry. Go ahead.
Sorry.
I was thinking like calibration events might require you to revisit, and like do if one of those steps is like a compile, and then you sort of, like you say, a loop. But what are you manifesting that as a direct event, or is it just, you guys already have a primitive that maps these events, and you can just trigger
For
off
now
of it?
we don't. For now we don't have the primitive for this kind of events, but I think it could be modeled as a kind of a loop, and then you need to have event to trigger the loop. So I would say,
Because that would be, it seems like it'd be an interesting use for this that are specific to
Mhm.
the quantum devices. So you could use that to have yet another way to sort of leverage this workflow that's really dynamic.
Yes. Yeah, we started by this very simple, let's say, more or less simple example. But then going further, we are realizing how it can be extended. So we are going one by one, in all directions we are thinking about, as I mentioned.
Very cool. Well, we're almost to the top of the hour. Wanted to give anybody else who's lingering back there, if you have another question, please raise your hand. Otherwise, going once, going twice. All right. Thank you so much, Doriana, for your talk today.
Thank you.
And one question that came up earlier was if we would be posting the video. That's usually up to the presenter. So if you mind, do you mind if we post the video?
No, no, it's okay for me. Yeah.
Okay.
You
Thank you.
can post, yeah.
Great. All right. Well, thank you very much. And with that, we will conclude for today. And thank you again.
Thank you.